Hey students, today we are going to learn how to draw the chair conformation for cyclohexane. This is not only a very important learning objective for H3 chemistry, it's also very important if you decide to pursue university level chemistry, even all the way to graduate school. Okay, so without further ado, I'm just going to represent or show you the representation of how we normally will draw cyclohexane on a flat piece of paper. I'm going to do that on the board first. So you're going to represent it with a 6-membered ring like this. Okay, so on the board is flat, but let's not forget that each of the carbon is actually sp3 hybridized. So for sp3 hybridized carbon is actually tetrahedral in geometry. So if it's tetrahedral in geometry, I'm going to use a Darling model to give you the illustration. So the Darling model basically consists of two pieces of something like a Lego piece, but not exactly a Lego piece. So I'm going to just put them together. Yeah. So when I put them together, right, this would be a sp3 hybridized carbon right in the middle. Okay, so you can see the tetrahedral geometry quite prominently. Okay, so I think it will be pretty clear to you, let's say, in what you learned for stereochemistry under introductory organic chem. If this is a piece of imagine this is the paper. So if I'm going to put this two bond on the paper, then I'm going to have a group projecting towards you. So this is the one projecting towards you, and then the other group will be projecting away from you at the back. Okay, so I hope you can see this quite clearly. So this is the tetrahedral geometry for methane, in that case, for a normal sp3 hybridized carbon. But what about for a 6-membered ring? So how will it look like? Okay, so right now I'm going to assemble them. So with two coming together, that will be ethane. Okay, and then I'm just going to slowly assemble them. So 3, and then I'm going to have 4, 5, and then I'm going to have 6 over here. Okay, so this is not so easy to assemble at certain points, so we need to change a bit. Okay, right. I'm just going to join both ends together. Okay, yeah, so you get like a 6-membered ring cyclohexane. Okay, but I'm just going to show you the most stable conformation. So I'm going to shift my position around a little bit so you get to see the so-called the chair conformation. Okay, so I'm going to shift this a little bit over here. Okay, all right, something like this. Okay, so do you see the chair conformation right now? So right over here, this is like where you put your legs, and then this is where you get to rest, and then after that, this is the position. Okay, sorry, I think it's over here. Yes, this is the position where you put your back. Okay, so I think you can very clearly see the chair conformation. Okay, so right now what we are going to do is we are going to try to draw this on paper. Okay, so in this case the paper will be the whiteboard over there. So that's the paper. We're going to replicate this structure, okay, the exact structure which you are seeing right now on the whiteboard. Okay, if you want a little bit of challenge, you can pause now and then try to draw this. Okay, so let me just put it still for maybe a minute or two, maybe not a minute or two, but a few seconds. Okay, try to draw this on a piece of paper right in front of you. Okay, so after you have done it, you can compare to the structure which I'm going to draw on the whiteboard. Okay, so right now I'm just going to move over there so as to draw the structure. Okay, so I'm going to take out the marker. Okay, so over here, this part is coming down, so it will look like this. Okay, and then after that, like this, and then I'm going to draw upwards like this. Okay, so basically this is the kind of chair that you are expected to draw for exams. Of course, this is not a perfect one. You can see that it's a little bit out of shape, but I think it's okay. Yeah, but one thing you need to take note of is that these two lines must be parallel. These two lines must be parallel, and then these two lines must be parallel. Yeah, but I want to urge you not to use a ruler to draw the chair because this defeats the purpose of you drawing it freehand, because the best chemists draw freehand. We don't draw with ruler. Okay, so once you have done the chair, so let me just erase this because I don't want to see the red marking. So after I'm done with this, I'm just going to draw the chair again. So like this. Okay. Then it's time for us to incorporate the groups in. Okay, so if you recall, maybe I'll take the model again. If you recall, right, there will be groups that are pointing vertically. Okay, so these are the vertical groups. So this is one vertical group, two vertical group, 3, 4, and 5, right? And 6 over here. Yeah, so the vertical groups are what we call the groups in the axial position. Okay, so I'm going to represent the vertical group with a a purple marker. So when you want to draw the axial position, remember that they alternates, okay, between up and down. So if this is going down, this will be up, okay, and if this is going down, this will be up, and if this is going down, and then this will be up. Okay, so it's exactly in the same fashion as what you might expect over here. Okay, so if I turn the thing a little bit, you notice that this is down and then up and then down over here and then up and then down and then up. Okay, can you see? It's exactly the same as the one I've drawn on the whiteboard. Okay, yeah, the one that is hardest to represent is actually those in the equatorial position. You'll notice that this equatorial bond is pointing, it's kind of like in this direction, 45 degrees up left, something like that. And then this is like pointing away, and then this is like pointing behind, and then this is to behind as well. And then after that you have this pointing 45 degrees upright, and then you have another one here. Okay, then how do we represent them on paper? Okay, so I'm going to use another marker. I'm going to use a red marker. Okay, so this is how we will represent it. Okay, so you point in this direction like this. Okay, can you see that this portion is like an inverted tetrahedron? Okay, it's like inverted tetrahedron. And then the one at the back, okay, is the tetrahedron that is upright. Okay, so it's a perspective thing. Okay, so let me just erase this. Okay, maybe I should erase the whole thing because it will be easier. Okay, so first I will draw the normal chair. Okay, maybe I should use another color because earlier on I used the black, so I think I should use black. Okay, so I have a chair like this. Okay, and then after that I use the purple line. So this is down, this is up, and then this is down, and then this is up, this is down, and then this is up. Okay, then now I'm going to use the red marker. So this is up, and then down, and then up, and then down, up, and down. Okay, now again, as I said, it's a perspective thing when we say up and down. Okay, so the axial bonds is pretty clear. So this purple bond is pointing down. The one at the back is pointing up. Okay, but the red one, right? In that case, you can visualize it as pointing up towards you. So it's not really vertically up. It's projecting out from the paper, and then this is going in. Yeah, but we're not going to show stereochemical perspective when we try to draw a chair. Okay, so I think this is a good enough drawing. And then, of course, for cyclohexane, you need to put in all the H's if you are showing this, because if not, people will think that they are methyl groups. Okay, you need to put in all the H's. So I think something like this will make sense. Okay, so in short, this is the drawing of the chair conformation, which you need to know how to do it. And then when you're in doubt, please practice it, because I think a good drawing of chair will go a long way in your studies. Okay, then some students have issues in showing some of the groups in projection. So maybe over here I will give you a little shortcut. Okay, now you'll notice that over here, right? this particular axial bond. If I'm going to just use the purple marker to write in, maybe I shouldn't use purple, I should use blue. You'll notice that there's a W shape like this. Okay, so I'm going to do it. There's a W like this. Can you see? Yeah, so this is like that. Okay. Then the other side, this is like an M. Okay, like this. Okay, so it looks like this. Okay, I hope you can sort of use this as a way for you to remember where should the axial bond of particularly these two carbon is pointing towards. Yeah, because normally the students have issues with these two carbons in terms of the way the axial bond should be pointing. Okay, yeah, so so in short, I think the drawing of chair conformation needs a lot of practice. Okay, so the first thing, maybe just a little bit more revision for you. The first thing you need to do is you need to try to visualize the chair conformation, and then after that, sketch it out. So it will look like this. Okay, so this is the usual chair which you will draw. Okay, and having learned Newman projection earlier on, right? Let's try to draw a Newman projection based on this chair. So again, I will use the model to help you. Okay, so I'm going to just show you the model again. Now, okay, so I'm going to show you the exact same chair. Okay, so like this. Okay, so you'll notice that this particular carbon, right, is right in front of you. Okay, so I'm going to tilt the structure a little bit. Okay, I'm going to tilt it like this. Okay, so do you actually see that this is actually a staggered conformation? Yeah, can you see this carbon in front of you? Okay, so this is the H here, H pointing down, and then the bond is going to the back carbon, and then after that there will be a group pointing up, and then another group pointing away like this. Okay, so if I'm going to number the carbon, okay, so let's say this is carbon number 1, 2, 3, 4, 5, 6, right? Okay, so what's going to happen is that I'm going to draw in the H's. So the H is here, the H is here, and then the H is here, and the H is here. Okay, so with the same idea, right, I'm going to draw the Newman projection over here. So like this. Okay, so this is right in front, and this is carbon number 1. Okay, so H is here and H is here. Okay, and then behind, which is carbon number 2, this is where the H is. Okay, and this is where the H is. So the H is here and the H is here. Okay, and then after that, I'm going to connect to carbon 3 and 6. Okay, so carbon 3 and 6, so 6 will be over here. Okay, and then 3 will be over here. Okay, and then after that is going to, oh sorry, I think there's a slight mistake over here. So 6 is actually here. Okay, and then 3 is over here. Okay, and then when we move across, we are looking at this region. We are looking at carbon 4 and 5. Okay, we're looking at carbon 4 and 5. So for carbon 4 and 5, what we are going to do is the easiest way, of course, is to connect with 6. So we are just going to draw this, and then we draw a circle. Okay, and then of course 5 is over here. So when 5 is over here, we'll just put this as 5, and then we point down. Okay, so once we do that, you know that this is the H we are talking about. Okay, so this is the H over here. And then carbon 3 bond to carbon 4 right at the back, like this. And then after that, up and up. And then of course, we are looking at these two H's. Okay, so the two H's are over here. Yeah, so this is the way you can approach drawing the Newman projection. Yeah, so if you try to recall, at the very beginning, we are trying to draw a chair conformation. Yeah, and then after that, we translate over to a Newman projection. Yeah, then you'll be wondering what are we going to do next. Okay, so the next thing, which quite a number of students also face a bit of challenge, is regarding the flipping of the chair. Okay, so you know that molecule is not static, so they will vibrate and then about their fixed position and then in constant motion, even the bonds. So they will try to attain the most stable electronic or energetically favorable state. Yeah, so of course, for a normal chair like this, for a cyclohexane, it's not really a major issue. Yeah, so the issue normally will come when we are looking at substituted cyclohexane. Okay, so for the simplest example, I'm going to use dimethyl cyclohexane to illustrate this. Okay, so I'm going to erase this first so that it might be less confusing. Okay, so I'm going to erase this. Okay, so I think I'm just going to draw a cyclohexane out and then maybe show you the stereochemical projection. So this will be a methyl group. Okay, maybe I should write OH. That might be slightly easier, and it's also similar to the model I have. So this is projecting into the paper. Okay, so something like this. Okay, so right now, again, I'm going to use the model. So it's the same model I'm going to use. Okay, but I'm going to put in the substituent. Okay, so what kind of substituent am I putting in? I'm going to put in the OH substituent. So, okay, so oxygen is normally represented with red. So I'm going to put one on top like this. Okay, and another one below. Yeah, you can see that this actually represents the opposite configuration, or they are pointing in opposite direction. So maybe I should shift my position a little bit so that you can see maybe clearer like this. Okay, so this is the normal chair we're looking at, and then the two OH are in the axial position. Okay, maybe I'll just pause here for a while for you to take a look. Okay, so right now I'm going to draw this exact conformation on the whiteboard. Okay, so I'm going to draw this so it will look like this, and then the OH one will be pointing down and the other one will be pointing up like this. Okay, you might notice that this conformation is not exactly very stable. Okay, then you might be wondering why is that the case lah? It's not very stable due to this, because you notice that the OH group is pretty bulky. Okay, so it will actually interact unfavorably with the axial hydrogen nearby. So like this. Yeah, so it will interact unfavorably. This is known as 1,3 diaxial interaction. Yeah. So this is repulsive in nature. So the repulsion will actually destabilize this particular conformation. Yeah, so because of the destabilization, this chair conformation will undergo what we call a ring flip. Yeah, so I'm going to demonstrate to you how a ring flip look like. Okay, so I'm going to go over here. Okay, now just to ensure that you are able to see what I'm doing. Okay, so now, yeah, so this is the chair which we have. Okay, so I'm going to do a ring flip, and once we do the ring flip, I want you to let me know whether you can tell where will the OH substituent be pointing towards. Okay, so please remember this. The carbon in front of you, okay, is pointing down. The carbon behind, or rather the OH behind, is pointing up. So the OH in the front carbon is pointing down. So I'm not cheating. Okay, so if you look at the structure, it's the same. OH here and then OH on top over here. Okay, now I'm going to do a ring flip. This is not a magic show. Okay, so although I think my hand is blocking, but I'll try to do it like that. Okay, so I'm going to do a ring flip. Okay, now when I do a ring flip, what's going to happen here is this portion I will flip it downwards, and then this portion, so this particular portion I will flip it upwards. Okay, so I repeat, this portion I will flip down, and then this portion I will flip up. Okay, so now watch, this is what's going to happen. Okay, what do you notice? Did you notice that now the OH group in front of you is still pointing down. Do you notice that? Okay, and then the OH behind is now still pointing outwards, but they are now in the equatorial position. Okay, and then you notice that your chair is now let me just, okay, oops, my apologies. Yeah, something like that. Okay, so let me just rotate it for you to see. Okay, maybe I should do it again. So okay, so this is the normal one. I mean the one you saw just now. Okay, just give me a while. Maybe I should change this so that it's clearer for you. Okay, so that because sometimes the model is a little bit loose when we do the flipping, it's not very convincing for students. Okay, right. Okay, so yeah, so back to this. Come, let's take a look. Okay, so like this. Okay, so again, let's try again. OH front carbon pointing down, back carbon pointing up. We'll do a ring flip. Ring flip means here I flip down, the one at the back I flip up. Okay, so watch this. Okay, so I have done a ring flip. What do you notice? Okay, you notice that now the one in front, the OH is in the equatorial position. The one behind, the OH is also in the equatorial position. So when you do a ring flip, whatever group that is in the axial position will now take on the equatorial position. Whatever group that is in the equatorial position, so earlier on the H is in the equatorial position, now is in the axial position. You can see that this H and this H, now one is pointing up, the other one is pointing down. If I flip it back, can you see that this H is equatorial, this H is equatorial, OH axial, OH axial. Okay, so I flip again. Okay, like this. Okay, so yeah, so this is what you get. Okay, so can we try to draw this conformation? So let's try to draw this conformation a little bit. Okay, so I'm going to rotate the structure such that you can draw up. Can you try to draw this particular conformation now? Like this is now like this, and this is now pointing down. Okay, yeah, so we'll try to draw this conformation after we do the ring flip. Okay, now take maybe half a minute to try to draw this. Okay, conformation before I draw it on the board. Okay, I'm going to just put it here for half a minute. Okay, yeah, right. So I'm going to draw it on the board right now. Okay, so usually we represent with an equilibrium arrow. So this is a long equilibrium arrow because the right hand side is more stable. This is a shorter arrow. Okay, I'm going to number it. Okay, for easy referencing. So this will be carbon 1, 2, 3, 4, 5, and 6. Okay, remember just now I was saying one of the group flip up, the other one flip down, right? So now carbon 1 flips up over here. So this 1, and then carbon 2, and then the other group is pointing down, something like this. So we have 2, 3, 4, 5, 6. Okay, then remember that whatever group that is pointing upwards in the axial position will now be found in the equatorial position. Okay, like this. Okay, then whatever group that is found in the axial position, in this case the OH, okay, it will now be at the equatorial position as well. Okay, like this. Okay, so this is what you're going to end up with when you are doing a ring flip. Okay, but a very important detail I thought I should highlight to all the students out there, right, is that when we do a ring flip, the configuration of the carbon doesn't change. Okay, what do I mean by the configuration of the carbon doesn't change? Okay, you'll notice that carbon 4 has the OH pointing up and the H in the equatorial position downwards, right? Can you see that at carbon 4 here, it has not changed? Okay, the OH is still pointing up. And then in this case, maybe I should draw in the H for completion. Okay, so the H is pointing down. Okay, and for carbon number 5, the OH is pointing downwards. This is still pointing downwards, and the H is pointing up. Yeah, so remember that when you do a ring flip, the configuration doesn't change. This is very, very important for students to recognize. Okay, so let us just use the model again to see whether what we have drawn makes sense. Okay, so you can take a look at this. Okay, so this is the group. This is, in that case, this is carbon number 4, OH in the equatorial position. This is carbon number 5 with the OH at the equatorial position as well. And then the H is up. Okay, carbon number 5, H is up. Okay, and then for carbon number 4, the H is pointing down. Okay, so I hope you will find the translation between the whiteboard and the model very useful in your understanding. Okay, yeah. So next, I'm just going to run you through an example to do a ring flip so that you are able to draw the correct, maybe the more stable conformation and at the same time with the correct configuration. Okay, so this is usually a problem that students have when they are doing their tutorials or working on assessment questions, and it's often asked, and the students need to do quite a number of ring flip, and then sometimes they get confused. Okay, so right now I'm going to erase it first. Okay, just going to put in some random groups so you have a bit of idea about kind of like what to expect. Okay, so right now over here I'm just going to put in maybe a CH3. Maybe I should write black. Okay, maybe a CH3. Okay, and then at the same time I should draw a projection in, and then maybe a CL. Okay, something like this. Okay, now I don't know what is really the best way to do such a question, because what is best to me may not be best to you, but what I can share would be what I will do if I'm you. Okay, so the first thing I will do is I will number the carbon, because that really helps. So 1, 2, 3, 4, 5, 6. So I will number the carbon in a clockwise fashion. If you wish to do it anti-clockwise, that's fine. Okay, doesn't really matter clockwise or anti-clockwise. Okay, yeah, but we need to have we need to signpost the carbon a little bit so that when we draw the conformation, we are sure that we are drawing the correct configuration at the carbon rather than its mirror image. Okay, then the next thing I'm going to do is just to draw a chair first. Okay, after you draw the chair, right, you can number the carbon if you wish. Okay, but maybe not if you wish. I think you should number the carbon. Okay, you can either be strategic about it, okay, or you can do it randomly. So let's say now, okay, I'm just illustrating an example now because I'm a little bit more experienced, so I can be a little bit more strategic about it. So I'll number this as carbon 1, 2, 3, 4, 5, 6. Okay, and then I'm going to draw the OH like this. Then I'm going to draw the CH3 pointing down like this. And then of course I have a CL pointing downwards like this. Okay, yeah, so you notice that I have two substituents in the axial position and then one substituent in the equatorial position. So this is definitely not going to be ideal. Okay, because there will be unfavorable 1-3 axial interaction between the two axial groups. Yeah, so I'm going to do a ring flip in such a way that I'm going to put the substituents on carbon 1 and 2 into the equatorial position, and then the substituent on carbon 3 into the axial position. Then some of you might be asking, can we put everything in equatorial position? No, this is not possible, because whatever conformation you draw has to agree with the configuration given to you. You cannot design your own question. Remember this. Okay, so right now we're going to do a ring flip. Okay, we're going to do a ring flip. And then after the ring flip, it will be good to number the carbon. Okay, so you can number the carbon as, maybe I should redraw this a little bit so that it looks nicer. So I'm going to number the carbon. Okay, so so same thing. This is going to flip downwards, so this will be carbon 1. Make sure that when you number, it's also clockwise. Yeah, you must follow this. Okay, remember that. Can you see that when I number it as clockwise, this is also clockwise? Can you see that? Yeah, so this is a way to check your answer. Yeah, so I have to number it clockwise as well. So 1, 2, 3, 4, 5, 6. Okay, and then of course the substituent must be pointing in the appropriate direction. So in this case, this will be OH. Okay, like this. And carbon number 2, the CH3 pointing down. So this is the CH3. And then for carbon number 3, the Cl is now projecting downwards. So Cl is like this. Okay, so this will be the answer which I'm going to submit for the most stable conformation. So I'm going to just show you that it's actually anti-clockwise as well. So this is fine. Okay, some of you might be asking, oh, what if at the beginning I am even better? I can input the groups into the correct configuration. Then I'll say, yeah, that, well done. I mean, that's a good job, right? So okay, so I'm going to give you an example. So let's say I'm going to draw in another chair configuration over here. Okay, and then I'm going to number the carbon. So instead of numbering this as carbon number 1, right, I put this as carbon 1. So this 1, 2, 3, 4, 5, 6. Okay, so when I do that, right, you notice that your OH is already in the correct conformation because it's now pointing upwards. And then the CH3 is now pointing downwards. And then the Cl is now pointing downwards as well. Yeah, do you notice that? So once you notice that, then you can also submit this as your answer. And then some of the students will be thinking, are these two the same? Yes, they are the same. It's just a different way of looking at a molecule. So maybe I can show you. Yeah, but I don't have so many substituents. But I think I'll just show you using whatever I have. So we'll just imagine that the CH, the OH is okay. So I'm just going to imagine the OH is like this. Okay, and then the CH3 is pointing down. Okay, I'm just going to show you the most stable conformation, not the one with the ring flip. And then I don't have a Cl here, but I'll just pretend that this is the Cl, although this is not the Cl. Okay, I'll just pretend that this is a Cl. Okay, okay. So it's a perspective thing. Okay, so the structure over here, it's really this. I don't know if this is clearest. Yeah. Okay. Okay. I'm not changing anything. You notice that I'm not changing anything. My hands are fixed. It's not a magic trick. Okay. So this is the Cl. Okay. I mean, I'm just pretending that this is a Cl. Okay. Now, so this is the conformation that we are looking at. Okay. Sorry, I need to take a bit of time to get used to because I'm looking at the screen right now as well. Okay. Yeah. Okay. Yeah, so this is what I'm drawing on the rightmost. Okay, can you see? This is what I'm drawing. So this is the Cl pointing down. This is the methyl group going here. Okay, and then this is OH equatorial. So equatorial, axial. Okay, so right now, right, some of you might be asking, what about the structure below? Okay, the structure below is simply this. Okay, I'm just going to rotate a little bit. Not flipping, rotation. Okay, I'm just going to rotate the structure a little bit. Okay, like this. Can you see that? Okay, can you see? The OH is now behind me, going in. Okay, and then the CH3 is like this. And then the Cl. Okay, so please pretend this is the Cl. I know it's not the Cl, but this is just pretend that this is Cl, okay? Yeah. Okay, can you see? So actually, these two structures, they are the same thing. The only difference is the perspective. Okay, can you see? It's the perspective. Okay, so it's like a rotation like this. Yeah. Okay, so it's basically about a 60-degree rotation. Or 45 degrees for that matter. Okay. Alright. Okay, so I hope through this exercise, you are able to sketch out the correct conformation, and of course configuration as well. Yeah, and do not have the misconception that all the groups must be equatorial position so that I can minimize 1,3 diaxial interaction, because this is definitely not the case. Okay, yeah, so that will be the end of this particular video, trying to show you, I think, number one, how to draw the chair conformation of a cyclohexane, and then number two, showing you the ring flip process, and then of course I think before that I show you how to draw the Newman projection for the chair conformation, and then of course after that I show you using the 1,2-dihydroxyl cyclohexane, how to actually do the ring flip to get a more stable conformation. And then I ended up with giving you an example with a fixed configuration. How do you actually translate between the different conformation? And then should you start off with the wrong conformation, you can always do a ring flip. Okay, but if you are very strategic, more strategic than me, you can just start off with this, with the correct numbering, and then straight away get the correct conformation, and of course the configuration as well. One of the mistake which your seniors often make is they drew the, maybe can I say they drew the correct conformation, but they actually drew the mirror image, and therefore they are marked wrong. Okay, so remember that in assessment, it's important to draw the correct structure, and we are often very sharp in recognizing that. Okay, I hope you will find this useful, and then do expect more of such explanation videos in the future. Thank you very much.